So guys, here we continue with the time domain analysis. After presenting the first order systems and the second order system analysis, we'll go to Ariel system. It's of course based on an nth order. So for such systems, we have first to check if both poles have negative real parts. In fact, we have, in other terms, we have to check if the system is stable, because if the system is not stable, it doesn't worth to go through the time domain analysis. So whenever we have all systems with negative real parts, here we have three different case studies. The first one is when all poles are real. So we'll approximate the system by the pole which is the closest possible to the real axis. The second case is if we have one complex conjugate pair of poles and all the other poles are real. So we'll approximate the system by this complex conjugate pair of poles. And the third case is a combination of the two previous cases. So if we have more than one complex conjugate pair of poles and other real poles, we'll approximate the system by the complex conjugate pair of poles which is the closest possible to the imaginary axis. A main remark is that in order to have a good simplification or a good simplified system, the remaining poles which are not considered in the simplification must be far from the simplified pole. The zeros must be close to this dominant pole, and we have to take into consideration the value of the gain of the system. So here we will present the first case study. In fact, we have a system of order 3. We have one pole, 3 zeros. When doing the PZ map of the poles and zeros, we found that we have two complex conjugate zeros, a real pole and one real zero, all have negative real parts, thus the system is stable. So we'll approximate this function by the complex conjugate pair of poles. This approximation must be good. The remaining pole is far from the complex conjugate pole, and the zero is near this pair of poles. So if you want to calculate the approximate transfer function, we get the following. In fact, from the pole and the simplified pole and zero, we maintain only the constant values which represent the gain, and we have these two plots for the exact function and for the approximate function. And when these two outputs on the same plot, we can compare between the behavior of the real and the approximate system. So we can see that the system behavior is almost the same. In fact, we have some small changes at the level of mainly of the peak and the response time, but we can see that the settling time and the error are almost the same for both systems. And here we have a second case study. In this case study, we have a pole at -1, a zero at -1. We have two complex conjugate pair of poles. The first one represented by the pole S2 plus 2. So in this case, the real part is null, and the second one is represented by S2 plus 3 S plus 10. So we'll approximate the system by S2 plus 2, but I will leave for you the approximation and the comparison between the exact system and the approximated one. The last part of this chapter will be focusing on the error calculation. In general, the error is defined by the difference between the output and the input, and the input represents the desired output. In fact, we can calculate this instantaneously or after each simulation. So E of t or epsilon of s is the value of the error at each iteration. Thus, as we have already discussed, E of t or E of s. And of course, in order to calculate the error, we need the closed loop transfer function system. However, in fact, based on this open loop transfer function, we can define three types of systems: type 0, type 1 and type 2. The type is mainly defined with respect to the number of pure integrators in the system. An integrator is represented by 1 over S. So if we have 0 integrators, so J equal to 0, we have a system of type 0. If we have 1 integrator, we have a system of type 1, and 2 integrators, we will have a system of type 2. So for a step input, the error can be calculated as following. It is equal to 1 over 1 plus limit for S equal to 0 of the open loop tensor function. So G of S, K of S is the open loop. As for the velocity error, it is calculated as being 1, or R. I'll discuss later on what is the value of R. 1 over limit of S times the open loop when S is equal to 0. At the end, for the parabolic input, which is when we have the input 1 over S3, it is equal to 1 over limit S2 times S squared times open loop when S equal to 0. The R is in fact the value of the gain of the input. If we have a step input which value is 1 over S, so the R will be equal to 1. So this table represents briefly the output that we have obtained. For a system of type 0, which is the most frequent system, which doesn't contain any integration, for K, we'll have Kp equal K, and the error will be R over 1 plus K. For type 1, we'll have the error, the static error or the position error will be equal to 0, the velocity error will be equal to R or 1 over K, and the acceleration error will be equal to infinity. As for type 2, we'll have the position, the velocity errors will be equal to 0, and the acceleration error will be equal to 1 over K. So also here we'll present a case study. The system is a system of type 0, 9 over S plus 1. So the open loop tensor function is 9 over S plus 1. The error will be equal to 1 if we have a step input, of course. It will be equal to 1 over 1 plus limit of 9 over S plus 1 for S equal to 0. So it will be equal to 1 over 1 plus 9. It will be equal to 1 over 10. Thus the error will be equal to 0.1 or to 10%. Of course, we do not calculate the errors unless the system is stable. For the velocity and the parabolic inputs, the error will be equal to infinity. Another case where the system is of type 1. So in this case, directly when we have a step input, we will think that the error for the position error will be equal to 0. The velocity error will be equal to 1 over limit S times G of S, K of S for S equal to 0. So it will be equal to 1 over 10 of 100 over 10. So it will be equal to 1 over 10, which will be equal to 0.1 or to 10%. So as we can see here, the step error will be the error for a step input, the position error will be equal to 0, the velocity error will be equal to 0.1, and the parabolic error will be equal to n.